All right, guys, so we are going to start Chapter 10. Chapter 10 is about gas laws, and I know I've read a lot on the page already. Honestly, I'm just going to talk through it. These are kind of the ground rules of the assumptions we're going to make during this chapter to make everything as easy as possible. So this is something called the kinetic molecular theory of gases, which sounds way more complicated than it really is. Essentially, all it comes down to is when we talk about gases, we are going to assume that it is mostly made of empty space. We're going to assume that basically it's a bunch of particles moving really quickly all over the place in a pretty random motion. We are going to assume that every particle is moving in a straight line unless it hits the container and bounces off, or hits other particles and bounces off. But we're going to assume that all the collisions are elastic. They're not going to like hit and stick together. Visualize it like billiard balls or pool balls where they're going to hit and bounce off. Okay. And we're going to define temperature as being like directly correlated to how fast the particles are moving. So faster movement equals higher temperature. Okay, really easy. I don't need you to memorize this, but these are the assumptions that we're going to be making for this chapter. Okay, so one of the first things we need to talk about when we talk about the gas laws is we need to introduce the idea of pressure. This is a new unit that we haven't dealt with in other chapters. Yes, I get that in real life you're dealing with all sorts of pressures in your life, but we needed to like officially define this in physics contexts here. Pressure is force per unit area. And if you physics people are like, yeah, I get this. Everybody else is like, that means nothing. So what I'm going to tell you is that basically the way you can visualize it is if these particles are bouncing around, if you have a container, it's how hard they're hitting the container and pushing out per unit area, how much force they're applying. Okay. So the units of pressure get a little weird. Okay. The units of force are newtons, but that translates to kilograms per meter per second squared. And area is meters squared. So what this all translates to is the units for pressure. The SI units, for any of you physics people, the default answer is a Pascal. Yes, this is the same guy who did Pascal's triangle. All that stuff, factoring polynomials and such. Anyway, 1 Pascal is equal to a Newton per meter squared, or you could visualize it, it'd be a kilogram per meter second squared. The units get a little weird. Okay, I will tell you that a Pascal is a really small unit. We actually saw it in a lab not too long ago, and we used kilopascals, and typical atmospheric pressure that you're breathing in is about 100 kilopascals. We'll actually get the explicit number here in a minute, but one of the big problems with pressure is that there's a lot of different units. It depends on what context you're talking about. Okay, I briefly want to talk about atmospheric pressure and just how we can visualize this. So atmospheric pressure. So crappy picture time, sorry. Surface of the Earth, some sort of atmosphere above it, right? You could visualize pressure being its force per unit area. You could have an area of the ground, and it's literally the weight of all the molecules straight up until the atmosphere ends. Okay? It's the force from the weight pushing down. Okay. This is why also if you ever go up like on a mountain, this is why it's harder to breathe up there. There's literally just less air. Okay, so whatever the height is, basically the stack of molecules, you've gotten rid of it's denser, it gets denser as you go down. You've gotten rid of the dense part, so that the amount of air pressure is going to drop. Okay, so here's the inherent problem, is the units get messy. I'm going to try to simplify this as much as I possibly can. Okay, so this weight of air at sea level on a nice sunny day with no major storm fronts coming through, somebody decided that this was going to be equal to 1 atmosphere, 1 ATM, okay? In chemistry, we really like this unit because we like setting things equal to 1. This is equal to 101,325 pascals, which is an indication that pascals are a super inconvenient unit to use. We usually write it as 101.325 kilopascals, but even that's pretty miserable. Okay. These are not the only options. There is a device called a barometer that measures pressure. Okay. Probably heard of barometric pressure. Okay. The original barometer was set up like this, and I'm giving you a little bit of history so that I can give you context for the weird units that are going to come out of this. So what you do is you take a dish and you fill it with mercury. Why mercury? Because apparently people don't care that it causes brain damage. What you do is you take a hollow tube, and what happens is, as the air pushes down, the only place for this mercury to go is up the tube. And so you can literally just kind of measure the height of this mercury. And the higher the air pressure, the higher this thing's gonna go, right? Seems pretty straightforward. But the units on this are millimeters of mercury. Okay, well, just because of the way that the density of mercury and the height of a millimeter, it turns out that 1 atmosphere is also equal to 760 millimeters of mercury. Atmospheres and millimeters of mercury are the most likely options for chemistry. Okay, pascals come up a lot in physics, but chemistry, and yes, you saw it in the lab, but chemistry, we try to avoid it if at all possible. We tend to pick one of these two options. Here's the problem. The general public is stupider than you could possibly imagine. If you tell somebody outside that the pressure is 760 millimeters of mercury, they're going to freak out that they're breathing in mercury, and they know mercury is bad for them. So, the general public does not like hearing the pressure described in millimeters of mercury. So, they just renamed it. We still go by millimeters of mercury, but they just renamed it as a torr. It is exactly the same thing, but people are dumb and don't want to hear mercury when they're talking about what they're breathing in. Also, probably should put this in there. This is also equal to 14.7 psi, pounds per square inch. If you're ever like worried about your car's tires, this is the units they probably use, psi. Okay. Basically what this means is if you had a square inch of ground and you're at sea level on a sunny day and you measured the weight of all the air in a straight line going straight up, it would probably weigh about 14.7 pounds. Okay. The important reason I'm pointing this out is that if you ever check your air tire pressure, you have a little pressure gauge, you just push it on there. If it's anything below 20, your tire's basically flat. Okay, it's not going to read 0 when it's flat. It's going to read 14.7 because that means it's equal to the surrounding pressure. The tire is trying to push back against the atmospheric pressure, so it has to be above 14.7. Okay, every car's a little different, but I would shoot for close to 30 at least. Upper 20s, lower 30s, probably in that range. But if you check your tire and you're like, oh, it's at 16, that's not, or it's at 14.7, it's not 0, it's not flat. This would mean that your tire is completely destroyed. If you try to drive on it, at least. So anyway, these are the units of pressure, and we are going to try to mostly deal with these ones, but I won't tell you that you won't occasionally see these ones. Sorry. Okay, thanks.